Our topic for today that we're going to discuss is more about vapor power cycles, in which the working fluid is alternatively vaporized and condensed. Steam is the working substance or the working fluid used in vapor power cycles, because steam, with its many desirable characteristics such as low cost, availability, and high enthalpy of vaporization. Steam power plants are commonly referred to as coal plants, nuclear plants, and natural gas plants, depending on the type of fuel used to supply heat to the steam. However, the steam goes through the same basic cycle in all of them. Therefore, all can be analyzed in the same manner. So, we will discuss the highest performance or the highest efficiency of a cycle, which is the Carnot vapor cycle, given the two operating temperatures. As a review, we have the two reservoirs given the high temperature. For example, this is our heat engine that will generate work, and this is our TL. So this is our QH and our QL. So we discussed or we derived the thermal efficiency, which is the work net over the Qn or the QH. So in terms of temperature, our thermal efficiency will be, this is 1 minus TL over TH. So this efficiency is the highest so far, based on the second law. In a machine that has the highest efficiency, then that Carnot cycle is a violation of the second law of thermodynamics. So we will evaluate the Carnot cycle if it is really applicable for the vapor power cycle. So first we will draw the TS diagram. The TS diagram for our Carnot cycle, that one. Okay, so this is our point 1 and this is our point 2 here, point 3 and point 4. Okay, the process 1 and 2, this is isentropic. This process 1 and 2. This is isentropic, and process 2 to 3 is isothermal, and process 3 to 4 is isentropic, and process 4 to 1 is isothermal. Okay, for this, the process 4 to 1 can be attained since this is below the critical point. Okay, so but the process 1 to 2, which is isentropic, we assume that is an isentropic for our Carnot cycle. This is the diagram for the Carnot cycle, the TS diagram. Cycle. Okay, so the steam expands here from 1 to 2. Then there is the quality of at point 2 is lesser than, or it has the moisture content at point 2 is of has a higher value. So for a turbine, the causes for erosion, the causes erosion for the turbine blades and can contribute to damage. It has only the limit. It has a limit of 90% quality. Or 10% moisture content. Beyond greater than 10% moisture can damage the turbine blades, so it cannot be it's impossible for this process from 1 and 2 to be applied in the vapor power cycle. Another thing, the process 2 to 3, this is isothermal, so we need to have a controlled quality. At what quality here at point 3, we're going to raise its pressure to the boiling pressure from here, and this is a mixture of liquid and vapor. So there's no device nowadays that can handle two phase, which is the liquid and vapor phase. Like for example, the pump. We know that pump handles only liquids. So if we will allow, or we are going to use the Carnot cycle, so we are to purchase a special pump that can handle liquid and vapor, and we have no special pump right now in the market. So in short, the Carnot cycle is impossible. It cannot be used in the vapor power cycle. Okay, so what we can do now is, since for example, for this one, this is the saturated liquid line and the vapor line here. So since liquid, it's a pump, so that one, and we're going to raise its pressure, the boiling pressure, and here to improve the quality of our steam, that one. Okay, as you can see, this is our 3 prime and this is our 2 prime. So in this diagram, we have ensured that the at point 3 prime, it's pure liquid. Okay, so as we going to draw its the diagram for this one, TS diagram. Okay, so okay, this one, this is our point 1, point 2, point 3, and point 4. This is our TS diagram. So this diagram here is what we call our Rankine cycle. So for vapor power cycles, Rankine cycle has the highest efficiency. So it is still ideal because we assume here ideal processes, like for example process 1 and 2 is isentropic, and this is 2 to 3 is isothermal. We have equal temperature, and process 3 to 4 is also isentropic. Okay, so we have now the diagram, that is diagram, the analysis for the Rankine cycle. So here's the ideal cycle for vapor power cycles, the Rankine cycle. So these are the components. You have a boiler, you have a turbine, you have a condenser and a pump. It is a loop. So and we have a mass here, mass of our steam, and we have the Qn in our boiler, and we have the work output in our turbine, and we have the work input of our pump right here. So to solve the efficiency for the thermal efficiency for the Rankine, this is simply the work net over the Q in. Okay, wherein our work net here is the work over turbine minus the work over pump. We have work input over pump. That one. Okay. So in terms of enthalpy, we have the efficiency over the thermal efficiency over Rankine. We have this work net over the Q n, or here this work over turbine minus the work over pump over the Q in, or this is, we have that enthalpy. In terms of enthalpy, we'll solve that one. I will derive in terms of enthalpy. So we're in our work over turbine will be this one, that is H1 minus H2 H1 minus H2, where our enthalpy is in per kilogram, and our WP, or the work over pump, will be this one. This is the work over pump will be H minus H, that is H is the work over pump, that is H3. Okay. That is H4 minus H3, and our Qn would be this one. We have the H1 minus H4. These equations, we assume that it is in the steady state, steady flow process. And we have the can assume that energy in is equivalent to the energy out. Okay, so our thermal efficiency would be in terms of the enthalpy, that is H1 minus H2 minus the work over pump, which is H4 minus H3. Over the work in, this is H1 minus H4. Okay, so we have also another equation for the pump. So review in our discussion, in our previous discussion, we have work over pump would be the V F3 This is pressure at 0.4 minus pressure at 0.3. Okay, so let's have now an example. Okay, so consider a steam power plant operating in the ideal Rankine cycle. Steam enters the turbine at 3 megapascal, 350 degrees Celsius, and is condensed at a pressure of 75 kilopascal. Determine the thermal efficiency of the cycle. So we have the given here. We have given pressure and temperature. Pressure is 3 megapascal, and we have the pressure and the temperature of 350 degrees Celsius, and we have the pressure at the condenser. This is the pressure P1. Pressure at the condenser is 75. We have this P2. We have 75 kilopascal. Okay, so going to draw it's the schematic diagram. This is our boiler here. And that's our turbine. And this is our pump. And this is our condenser. Turbine, this condenser, and this is our pump. We have a work input of our pump, and we have the QN. And turbine will generate its work. So we have, this is a loop wherein we have the mass of our steam. Okay, so based on the given from steam tables here, we'll find the values from steam tables. Or the Muller chart, or the enthalpy versus entropy chart, the HS chart. Okay, so this is our point 1, 2 here, 3, and 4. Okay, and let's draw its TS diagram for our analysis. Okay, so this is the TS diagram for our Rankine cycle, when we assume processes to be ideal. Okay, point 1, point 2, point 3 at this point, and point 4 at that point. Okay, So we need to find the values for H1, values for H2, H3, and H4. So H1 is the enthalpy at 3 megapascal and 350 degrees Celsius. We have H1 from steam tables, that is superheated. From superheated tables, we'll find the value. So the value would be let's try to look the value for that one. So that point here is 3. We have 0.075 megapascal, or that is H3 at this HF at this particular pressure. So H3 is this 384 per kilogram, and our V3 is the VF, which is 0.001037. This is in kilojoule. No, that is in meter cube per kilogram. Okay, so on the steam tables, our H1 would be the 3115 kilojoule per kilogram, and we have our H2. Our H2 would be 2403 kilojoule per kilogram. So we have H1 and we have H2. So you can also calculate the H4. How are we going to calculate the H4 here? So okay, there's no need to calculate the H4 because we have the work net now is work of the turbine minus work of the pump. Okay, work of the turbine, that would be H1 minus H2 minus work of the pump, work with the pump will be 0.001037 times the pressure 4 minus pressure 3, where pressure 4 is 3 megapascal, and that is 3000 minus 75. Okay, so we have our work net. Since this is very small, that can be negligible, so we have the work, or this is 3, okay, here. So the work net would be this one, 3115 minus H2 is 2403 minus this one minus 3, so this is 709 kilojoule per kilogram. That is the work net of our Rankine cycle. Okay, so we're going to solve also the Q in. Our Qn would be H1 minus H3. Our H1 is given. We have our H1 will be have our Qn, we have H1 minus H3. This is minus the work with the pump. Okay, so that is 3115 minus 384.3. 384, that is minus 0.3. Minus 3, I mean. So we have our Qn, that is 2728 kilojoule per kilogram. So we have the value of our work net and we have the value of our Qn. So we can solve now the thermal efficiency of our Rankine cycle. That is work net over Qn, and this is 709 over 2728. Okay, so that would be 0.2599, or that is 25.99%. So we have the answer for our Rankine cycle. We have 25.99%. As we're going to draw again the TS diagram for our Rankine cycle. Okay. That one. We have this 0.1, 0.2, 0.3, and 0.4. So we know that this is an ideal cycle for vapor power cycles, the Rankine cycle. And you know for a fact from our knowledge of the second law of thermodynamics, because of its irreversibilities. For example, the fluid friction causes pressure drops in the boiler, in the condenser, and in the piping in between. And for the various components, the heat loss from the steam to the surroundings as the steam flows through the various components. And the division of actual pumps and turbines from the isentropic ones can be accounted for by utilizing isentropic efficiencies. So or if we have the isentropic efficiencies, this would be like this one, this dotted line. And this would be my 2 prime. Okay, and this would be my 4 prime. Okay, that is the actual vapor power cycle. So also, as mentioned earlier, here, due to the losses that one should be our 1 prime, and also this one. That would be the should be the deviation for the actual versus the ideal cycle. So, but of course, we assume for our analysis, we assume that this is isothermal, but because it has no significant effect. But for the isentropic efficiencies, this would be the should be our diagram here, this dotted line. Okay, for example, we have given efficiencies for our pump, and we have given isentropic efficiencies for our turbine. Okay, so now that is the division for the vapor power cycle, actual versus the ideal cycle. Okay, so question, since Rankine cycle is the ideal, and we have some ways to improve its efficiency. Okay, so what are those ways? This number one is here, by increasing by lowering the condenser pressure. So we lower the condenser pressure. Okay. So when we lower the condenser pressure, this would be our that 1.1, 0.2, 2 prime. This is our 3. This is our 3 prime. And this would be our 4 prime. This is our 4. And this is our okay. This is our 4 prime here. Our 4, and this would be our 4 prime. So by this would be this area. This would be the increase in our work net. This area, if you lower the condenser pressure. Okay, so by merely looking at the diagram, since our thermal efficiency would be the work net over the Q added, or the Qn. So since the thermal efficiency would be proportional to our work net, so since there is an increase in the work net, so our thermal efficiency would also increase. Okay, so to illustrate that one, we will continue by, for example, we would lower the pressure from 75 kilopascal down to 10 kilopascal. Let's say 10 kilopascal. So we'll solve, therefore we're trying to show if it really if the efficiency would increase. Okay, this is our 75 kilopascal condenser pressure, and this would be our 10 kilopascal. we lower that one. Okay, so based on this steam table again, we have the H here, the H2 prime. H2 prime would be 2136 kilojoule per kilogram. So based on this steam table. Okay. So now we'll compute its efficiency if it's true that the efficiency would increase. Okay. So you have the work net. You have the work net, that is 3115 minus 2136 minus 3, and that is 976. This is in kilojoule per kilogram, and our WP, the work over pump, would be this 0.0010 101 times the 3 megapascal, that is 3000 kilopascal minus 10. Okay, and this is also 3. And we have our Qin is 3115 minus 192 minus 3. Okay, so that is 2920 kilojoule per kilogram. Okay, so we could compute the efficiency now. The efficiency would be 976 divided by 2920 times 100%. So this is 33.42. So it's true. Based on our previous example, so our efficiency is, we have the 25.99%. So it would increase, there's an increase from 25 to 33.42. So you can say therefore that the effect of lowering the condenser pressure would also increase the thermal efficiency. Okay, so but there's a limit in lowering the pressure for the condenser. That is its limit its limit would be the lower limit for the condenser pressure that can be used cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. So for example, you consider a condenser that is to be cooled by an early river at 15 degrees Celsius, allowing a temperature difference of 10 degrees Celsius for effective heat transfer. That's common. The steam temperature in the condenser must be above 25 degrees Celsius. Thus, we have 3.2 kilopascal, the saturation pressure. Okay, so P saturation, this is the lower limit. Okay, so this is 3.2 kilopascal. Okay, and its temperature would be 25 degrees Celsius. So again, the difference, the delta T here for effective heat transfer, that this would be 10 degrees Celsius. So if your the temperature of your river for the condenser is 15, then for example you have 25. So this delta T is our assumption for effective heat transfer. So this temperature and pressure would vary, depends on the source or the source of our water entering our condenser. So you have to maintain the 10 degrees delta T. Okay, so the effect of lower than this the saturation temperature or the saturation pressure would be leaking. There's a leaking, no? There's leakage for there would be air leakage for the condenser, and that air leakage would contribute to increase on the moisture content. And as we've discussed, the increase in moisture content can cause erosions in our turbine blades. Okay, so there's another thing. So we would superheat the steam to high temperatures. Okay, so what would be the effect when we superheat the steam? Okay, when we superheated one from this point to this point. Okay, point 1, point 2, this is point 3, and point 4, this is our 1 prime, this is our 2 prime. As you can see in our TS diagram here, if there is superheating in our steam entering the turbine. So as it expands, this would contribute in increasing our quality, since our quality x2 is lesser than the quality x2 prime, or x2 prime is greater than x2. Okay, so again, we would illustrate that by an example. For example, we would assume a temperature for 1 prime. For example, we have here 600. We have 600 here. We have a temperature of 600. Okay. So for our previous problem, the given would be 350. So this is 350 here. And this is 600. This should be in degrees Celsius. Okay, so this is our 1 prime. So 600. So again, our H1 prime at 600 degrees Celsius, that is 600 degrees Celsius and 3 megapascal. That is, in our steam table, when we look at our steam table, that is 3683 kilojoule per kilogram. Okay, so we'll compute again the work net. Our work net would be this 3683 minus 2380 minus 3, the work over pump, and that is 1300 kilojoule per kilogram. And our WP, that is still 3, it is 0.0001 0.00101, still the same, 0.00101 times the 3000 minus 10. Okay, this is 3. our Q would be, our Qn would be 3683 minus 192 minus 3. This would be 3488 kilojoule per kilogram. So our efficiency would be 37.27%. Okay, this is work net over Qn. Okay, so we have shown that by increasing the boiler or by increasing the boiler temperature or separating the steam inlet to the turbine, hence we have the increase of thermal efficiency. Now we have last condition. So by increasing the boiler pressure, you have to increase the boiler pressure now. So by increasing the boiler pressure, so we have to draw the TS diagram. That one. So increasing the boiler pressure, that one. At the same temperature. Okay. So the TS diagram to increase the boiler pressure here at 15 megapascal. This one. And this is our 3 megapascal. Okay. So by our TS diagram, by our steam tables, this is our 1 prime, so 1, 2, increase in area. So if there is increase in work net, so there is increase in thermal efficiency. So from steam tables, we have the value over H1 here. This is 3583 kilojoule per kilogram. Okay, you increase the boiler pressure from 3 to 15 megapascal. So we would compute now the work net. This 3583 minus 2115 minus 15. This is 1453 kilojoule per kilogram. Workable pump, that would be 0.001 0.00101 is 15,000 minus 10. So this is 15. Okay, and our Qin would be 3583 minus 192 minus 15. This is 3376 kilojoule per kilogram, and our efficiency would be here 1453 over 3376 times 100%. This would be 43.04 kilojoule per kilogram. Okay, so but we have 3 cases, and from 25.99%, this would increase to, if you lower the condenser pressure, this would be 33.42%, and if we increase the boiler temperature, that is 37.27%, and if we increase the boiler pressure, that is 43.04%. So an increase in work net would increase its thermal efficiency, as the diagram shows, and as based on our computation. So if you have questions, please just drop a comment below. If you have some clarifications, just leave a comment, and I hope to post another video for the next topic. Thank you and God bless.